Hi, I'm Shaun. I've just finished my PhD at the University of Southampton, and so today I'm going to be talking to you about some of the things that I've been doing over the last 4 and a bit years, looking at electrokinetics and electrokinetic remediation for essentially decontaminating radionuclides at nuclear sites. So I've been focusing mainly on difficult to measure radionuclides, so those are either pure alpha, pure beta, or low energy gamma emitters, or some combination of the three and seeing whether we could use electrokinetics to clean up sort of various materials at nuclear sites. So firstly, what is electrokinetics? So it's a the fundamentals are pretty straightforward for it really. The idea is if you've got some sort of contaminated material, so say for example there's some sand here, and you take the contaminated material, put a couple of electrodes in, hook those up to a battery, get an electrical current running through it, and when you do get that electrical current going, there's three main processes that can occur. The first one is electromigration, so movement of ions. So opposites attract in this case. Anything with a negative charge moves to the positive electrode. Anything with a positive charge moves to the negative electrode. You can also get electrophoresis, so that's movement of colloids, so small charged particles again, opposites attract, and so they migrate similarly to electromigration. And then finally electroosmosis, which is movement of water towards the cathode. And at both electrodes you also get electrolysis of water occurring. I've got the half equations down here, but essentially the bottom line is that you get hydroxide ions forming at the cathode, protons at the anode, and so because of their respective charges they move towards each other, and essentially you can form a pH gradient in your cell over time. So my work generally for the PhD, I've focused on three main materials: sediments, cements, and groundwaters. Today I'm going to be focusing on the sediments. I think that's the most interesting of the topics, but all of them have kind of presented their own kind of interesting findings. But as I say, for the sake of time, I'm just going to focus on that one area today. And that one area is a sediment core from the Ravenglass salt marsh in Cumbria. So the salt marsh is it's about 9-10 kilometers away from the Sellafield site, and as I'm sure many of you know, Sellafield, since it started operating in the 50s, has been discharging radionuclides into the Irish Sea, and whilst most of those dissipate and disperse into the oceans, a small amount of those then end up washing back up onto the coast, and areas where you have constant sediment accumulation. So, for example, areas like the salt marsh we've got here in the estuary, you can end up with areas of constant sediment accumulation. If you have radionuclides that like to stick to sediments, then those also then get buried as well, which can produce partial or whole preservations of the Sellafield discharge history, essentially. And so because a lot of this has been sitting around for years, even decades, in this sort of coastal environments, we wanted to see whether we could decontaminate it, basically see if we could remobilize those radionuclides that have been there for a long time. So on the right here we've got a sort of slightly neater setup of what the electrokinetics normally looks like. So I've removed the wires, but otherwise everything else is the same. So you can see these black bars, these are the graphite electrodes. We've then got two separate experiments here. So our core was originally cut into three. 1/3 of that was used to understand the initial conditions in the core. 1/3 was treated with Atlantic seawater as the electrolyte. Now, an electrolyte is basically something to keep the core damp so that you can allow the current to flow, you can allow your ions to flow as well, allow your ions to migrate. The idea with using seawater is that if electrokinetics was to be scaled up, and potentially if it was used in situ as well, then coastal settings, there's no easier liquid to get your hands on than seawater. So we wanted to see how well it would work in that case. And then the final third, we use citric acid as the electrolyte, the idea being that citric acid is a good chelating agent, and so is more likely to be able to mobilize some of the sort of slightly more stubborn radionuclides as well, compared to the seawater, but it's also biodegradable as well, so it helps. It's a better alternative than, say, using traditional chemicals like EDTA to try and remobilize some of these radionuclides. So there were four radionuclides I ended up looking at in the end. We've got americium-241 here. I've got two plutonium isotopes, 239 and 240 together. This was because they were measured through alpha spec, and so the peaks basically appear as one. So we've combined them. I did also look at cesium and technetium as well, but again, for the sake of time, I've not included those here. So in both cases, on the x-axis, we have the activity of the americium, the activity of the plutonium, and then the depth here is the depth of the core. So the core was about 54 centimeters in depth, and then this grey set is essentially the initial conditions. This is what was present in the core before being treated. So then we put our electrodes in. We have our cathode at the top, which is negatively charged, our anode at the bottom, and our cathode will produce alkaline conditions, our anode will produce acidic conditions, as I mentioned earlier. And we expected the americium and plutonium to move upwards. We expected probably a positive charge, the positively charged species, although it was certainly from EHPH diagrams that were very simplified. These were just the radionuclides in water. Even the plutonium, the jury was out. There's a lot of species that can either be positively or negatively charged. There's then also the citrate as well. Any citrate complexes would probably end up being negative in the case of the citric acid core as well. But so we weren't too sure, but certainly seawater core probably up towards the top of the core, citric acid probably down. So in the case of the seawater core, with the americium, first of all, you can see a really nice movement of the peak. There's very little left. There's a very small residual fraction that didn't want to move, but the rest of it has moved upwards, and it's probably likely stopped there because of the alkaline conditions produced by the cathode. So the pH data that we had suggested that the americium was fine in acidic and probably neutral conditions, but the moment it started getting alkaline, it just stopped and wasn't interested in going any further than that. By contrast, the plutonium, anticlimactic to say the least. Yes, it's not really gone anywhere, which probably wasn't much of a surprise. We knew that the plutonium was probably going to be pretty stubborn, and yeah, it's safe to say it lived up to its reputation. Now, moving on to the citric acid, the americium is very interesting actually compared to the seawater, because we'd probably expect the americium to expect the citric acid to be more effective at remobilizing than the seawater, but whilst the citric acid was still very good at remobilizing the americium from this original peak at about 30 centimeters depth, you can see that it's not as extreme as in the case of the seawater. We are assuming that is because in the case of the citric acid, you've only added citrate and protons, citrate ions and protons, or hydronium ions, and so what may be the case is that the americium, the citric acid is good at remobilizing the americium, but it still has a high affinity to the sediment, which may mean that it starts to migrate and then it sort of resorbs, and you get this resorption-desorption mechanism. And that might explain why there's no obvious peak. Instead, at the top part of the core, you just have this sort of continuous level of higher activity region there. In the case of the plutonium, we have much less noticeable decrease compared to the initial conditions, but we do see a decrease in the plutonium within this original peak. And what's also nice is we can see a peak as well, much closer to the electrode, although there is still this region of higher elevated activities. So it would be nice if we could ideally get all of that kind of right next to the electrode, but that, you know, is future work for someone who is not me, and particularly the americium. I reckon if we were to neutralize that, use seawater, because there's competing ions in the seawater, so hopefully that means when the americium moves, another ion is able to occupy those adsorption sites, and that may well be why the americium seems to move more in the seawater. If we were able to neutralize the alkaline conditions at the cathode, then I reckon we might be able to see some more movement right towards the electrode with the americium. So looking at electrokinetics in general, overall, looking at all my chapters across the sediments, groundwaters and sediments, I've created a sort of periodic table with different elements that I've looked at that are relevant to the nuclear industry and mark them on a traffic light system. So green is we've seen significant movement, pardon me, significant remobilization in at least one different material. Yellow is limited mobility or a little bit inconclusive as to whether it definitely works or not, or it might be that particularly in the case of the tritium, it might move, but it just takes a really long time, and you might be looking potentially at several months. We did find that with the groundwater. It moved a lot slower than, say, strontium and technetium. Not to say it couldn't work, but you may be looking at different sort of lengths of time scales depending on the problem. And then iodine, marked in red, needing further work. We looked at it in cements where, yeah, I think it got incorporated in mineral phases and didn't really seem to want to go anywhere else. But I think if we were to look at different conditions, different sort of context, different settings, I think we'd expect to see the iodine behave much more like we'd expect and see it be a lot more mobile than it was in our results. So overall, you can see here there's a lot of success. Obviously, more work that needs to be done. This is by hardly an extensive view of the periodic table. There's a few elements that I've marked in blue that I think could be interesting. They have isotopes that are relevant to the nuclear industry, and from evidence from the work we've had would suggest that these are mobile in certain conditions and amenable to electrokinetics. So that would be quite interesting to see whether those could work in future. So thank you very much. That's I'll leave it there. Thank you for listening. I've put my email there. Sorry I wasn't able to be here in person, but if you've got any questions, feel free to send me an email. I'm happy to answer them. Also, I believe my supervisor, Sir Andy Cundy, is part of the is in the session. So if you've got any real burning questions, he may be able to. He would probably be able to answer them. But if not, as I say, I'm also happy to answer any email questions as well. Okay, well, thank you very much for listening and enjoy the rest of the session.